Okay, cool. So today I would like to get started. Can you all see my playground? Cool. I want to get started with a binary search. So who can kind of give a loose explanation of what binary search is? Don't all
Is it
chime in.
is it when you are comparing one thing to another thing? I don't know.
Isn't it when you have like let's say you have a target number and you have like an array, so you would go through that array and you would have like a pivot. I don't know what the specific term is, and then that would be what you compare it to. So if the target number is higher than the middle number or whatever you're looking at, then you would go to the right side. If it's lower, then you would go to the left side, and then you would just repeat that process.
Yeah. Cool. So for example, in this array, Anthony, if I said find the number 7.
Right. So you would probably want to have it make sure it's sorted, which in this case that one is, and then you would break it down into the two parts. So it would be broken down into the left and right side based on the middle. So the middle in this case is 5. So then you would compare, is 5 greater than 7? No, because it's not greater. You would then go to the right side to look for it.
So that's great. So if we said, I want to find the number 7, the first and really important note is that the array must be sorted in order to perform this kind of search. And so if we wanted to search on an unsorted array, what would the time complexity of that be? We can't use a binary search. So what would the complexity be to search on an unsorted array? How do you think you might do that?
O of n.
Why is that?
You're searching through it iteratively. N being the number of items in the array.
Yeah. And so the worst case would be what if we use this kind of linear search? Like, can you explain the situation that would be the worst case?
O of n.
Yeah, can you explain it? Not the complexity, but actually, when would that happen?
If you go through the whole list and let's say, for example, the number that you're looking for is 9. So it goes through all the indexes until it gets the last index, and that's the one.
Right. So if the number is at the end, then you had to go through every element to get there. And then in terms of like decision making with code, this is where you start to talk about trade-offs. So every time I go to search on an unsorted array, it's O of n. I have to look through every item potentially if the thing is at the end, because there's no particular order. But what's the complexity of a binary search?
I'm just guessing, but is it log of n or yeah?
Yeah. So it's O log n. And we'll talk about exactly why that is. But like, what is O of log n? Like in terms of numbers, is that faster or slower than O of n?
Faster.
Mhm. So it's faster than O of n. And so if we could, we'd probably like to use binary search all the time. That's great. The thing about that is, however, sorting is, in most best cases, what is the time complexity of Swift's array sort? What do we remember about sorting? Like, what's really, hopefully, the best case we can get?
Is it O log n?
So it's not log n, actually.
I mean, I just checked the website and it says ON login.
Yep. So it's O n log n. So even, like, side note, even if you don't know the specific implementations for sorts, just know that the Swift sort is O n log n, and that's generally the best case for the best sorts that you see, or generally the average case for the best sorts that you see. And when we have compound terms like this, what that really means is n times log n, right? So the whole point of big O is we are charting out a growth. We're charting out how quickly the time complexity usually for this will grow. And here's where the consideration is. Consideration. Sorting takes more time than doing a linear search. But binary search, so the thing about log n, let's see if we can pull up a graph, is,
I have one. I have the one that Ben gave us.
yeah, do you want to share?
Yeah.
Or Slack it out, whichever you prefer.
Yeah.
Big O sheet. So this is a really great command. Know thy complexities. Do you see that? Do you all see a graph? Cool. So know thy complexities. What this is just saying is, here is a graph of all of the ways that these things grow. Where do you see log n? Where do you see O of log n?
In the green.
Yeah, so it's the green. So O of log n actually grows incredibly slowly. Incredibly slowly. And so log n is not nearly the same growth as n, because look at this. When you multiply n log n as opposed to n squared goes up really, really sharply. N log n still kind of grows almost in a linear way.
Can someone briefly talk about what log is again? It's been years since what, calc?
Yeah, I want to do that right now, actually. Just a quick one. So let's do, I'm just trying to keep this split up. Digression. Important one. What's a log? So a logarithm is a way of charting out exponents, actually. It's kind of like the inverse of an exponent, if you think about it. What a log is let's just do this. If I say log n is equal to 10, what this is denoting is that there is a hidden subscript here, a hidden base for log saying what my counting system is. So log n is equal to 10 is the same thing as saying, well, whatever counting pattern I'm using, like humans use base 10, but in code we use base 2, whatever counting pattern that is, that number to the 10th power is equal to n. And so what this converts into is 2 to the 10th power is equal to n. And that number is somewhere in the 1000 range. I think it's 124. And so when we talk about it in code, we're always talking about it. We're always using base 2 logs. So we're always saying that hidden subscript is 2. And what that means is that if we're talking about logs, the number that they're equal to actually grows really, 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 really slowly. Because for log of n to equal 11, it needs to, the input itself needs to be twice as big. So even though n got twice as big, it's literally 1,000 more. It took adding 1,000 more elements to the input to n to actually make the value of log n go up by 1 whole number. So log n grows really, really, really slowly in relation to the size of the input. What are some questions you have about that guy? Okay. So knowing that log n is actually usually a really small number, our goal would be, if we're in a situation where we only have to sort one time and then can binary search on it many times, it's to our advantage to do it, because rather than doing it linearly every single time on an unsorted array, if we sort it, it's more expensive than that single linear search. But if we now have that sorted and can perform 10, 100, 1,000 binary searches on it, it becomes much, much, much more advantageous for us to, in terms of time complexity, to be using that binary search. So if we only have to sort it once, and then we can do a binary search many, many times, then we're good, because binary search being O of log n means our complexity for the entire sort, search, as many times as I want. Eventually, the average for doing all those operations is faster than a linear operation. Faster on averaging all functions calls than O of n. How do we all feel about that right now? Sorry, I thought that was all you slacking me, saying I have so many questions, but that was not it. So we feel good about using a binary search. We like this. It's okay if you don't. All right. So we chose to use this on a sorted array. That's the important first step. Anthony, can you keep talking us through in a little more detail what you're doing with this splitting?
Yeah, so now that you have the array sorted, you want to find the point that you're going to use as the pivot. So you can get that from the count of the array divided by 2, which would give you the middle of the now sorted array.
Cool. And then with that middle, what do you use that pivot to do?
You're going to make the comparison. So you're going to compare the target number against that middle number. And then you're going to see if the target number is greater or smaller than the middle number. And that's going to denote which side that you go to next.
Yeah. We check to see if the number is greater or less than the pivot point. And then, Sam, can you take it from here?
Sure. You would just keep doing that same thing, depending if it's greater or less. If it's greater, we go to the right and split that array the same way from the middle.
Mhm.
And keep doing that till you have 2 numbers. And your target number should be one of those 2 numbers.
So what do you mean by have 2 numbers?
Could you go
Like
back?
the subarray is 2 numbers?
I'm not sure.
Okay. Well, there's one important thing here. There's one more if that's actually super important and makes this whole thing really, really simple for us. If the pivot, if the target number is greater than our pivot, go to the right side array. If it's less, go to the left side array. But there's one other situation. What's that situation?
If the target number is the pivot?
Yep. Return it, right? So if it's equal to the pivot, return it. Let's take a look at our example. So in this situation, what's the initial pivot? Albert, what's the pivot when I first want to do this?
The middle of the array
Yes, what's that value?
be 0, 1, 2, 5.
Cool. So we start at 5. Mhm.
Index will be 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it'll be index 4 and value 5.
Great.
Ugh.
So we got the pivot. Is the pivot our target? Absolutely not. Then is the pivot less or greater than our target?
Less.
Kevin, what's a?
Oh, sorry.
No, that's okay.
Less.
Less. So before we even do anything, what we know is that 5 and anything to the left of it are all smaller than our target number. So we can rule out 1, 2, 3, 4, 5, or indexes 0 through 4. And that means that we've cut the problem in half with just one operation. We've only done one thing. And now all we're looking at is half of the problem. So now since the target number is greater than our pivot, what are we going to work with now?
Indexes 5 through 8.
Yeah. Our array to binary search on is just 6, 7, 8, and 9 after one operation. Cool. Now, what should we do?
Get the middle index of that array.
Yeah. What's the middle index here?
7.
Cool.
Well, 1.
How could you, what's giving you pause?
No, just I was referring. I don't know if I was going to refer to the value or the index.
Okay.
Sorry.
So are you talking about the 7th index or the integer 7?
Integer 7.
Cool. At index 6. Okay. Why is that though? Like,
Oh no,
is that?
no, not index 6. Index 1, right?
Oh.
0. Oh, right. Total.
First array.
Yeah.
Index 1 in the subarray.
Okay, I see.
So this is actually a really important thing. When we're talking about indices on a subarray, those, depending on how you've split that subarray, if you've just copied the values from one array to another, you do start counting at 0. But if you use Swift's built-in, if we use Swift's built-in, I'll call it array slicing, the original indexes can be maintained. That's just an important note. I thought it's cool.
Is that the split function or is it something else?
No, so split, well, let's run it. Here's my array. Let split array equal this array dot split. Where do you want to separate it? Let's look back at that thing. Split returns the longest possible subsequences of the collection in order around elements equal to that given element. I don't know, let's try it. Let's see what it is. Print split array. Let's run it. Cool. So what do you see? What did it do?
It divided the array into before and after the number 6.
Yeah.
With this, we gave it to it in order. If it was not in order, would it have separate, ordered it and then handed it back?
Let's try it out.
Is the return type an array of array slices?
Yeah, can you say that again?
The return type is an array of array slices.
Thanks. This actually gives us an array of array slices. Cool. And Tia, to answer your question, what it looked for was literally just the value 6. It said, I will split there. Not really concerned about, it doesn't actually fit our binary search paradigm because it can work on an unsorted array. But one thing I just want to emphasize is when we split our array, well, here we got 2 subarrays. So if I print out the first of those, that's great. Now let's see if I can index this. Cool. So in the first array slice, which is all the stuff before this number 6, it seems to maintain its indexes. Again, split array at the first index is an array slice. And then if I add this guy back, it's going to give me the thing at index 1 there. However, let's look at this guy. I look at the second array slice, which is just an array with this value 7 in it. And so I would think I can look for the first index there. But that's not how array slices work. In the slices of this array, the original indices are maintained. So even though this guy has 1 element in it, that element is not at index 0. How can we find it? What index is it actually at?
8.
Yeah. Awesome.
Does this mean that a array slice is a type?
Oh yeah, absolutely. Check this guy out.
Cool.
My split array is literally an array of this thing called array slices.
Gotcha. Missed that.
Yep. It's amazing. Cool.
And does it maintain the original indices? Because what if we decided that the separator was 7, then we wouldn't have anything in the second array slice?
Well, let's see. Dang. But what's it actually going to give us?
1 array slice.
Yeah. And that's like literally because there is nothing.
Okay.
Yep. Cool.
Usually when I research, when I've done binary research in the past, I haven't really used the dot split. What I've done was have a left index and a right index, and then you would go from there. I'm just wondering if the dot split adds any kind of like time space complexity.
Okay. Actually, so this was kind of a digression again. Split isn't a binary search. But what this can do is, this example right here, if I want to talk about array slices, there's basically two ways to handle indexes for binary search. I could, one, do it numerically, like you say, where start with the value of the middle index as the pivot, and then determine if I need to go left or right, and keep doing that until I get my result. That's kind of what you're talking about, right?
Yeah.
Yeah. Another way of doing it that you will see is do it by actually slicing the array and performing the same operation on an array slice of that array.
So you would do the second one recursively, right? Or you
Yeah.
could do both recursively.
Yeah, we could do both recursively.
But in the second one, you'd be putting the array slice into that function.
Exactly. And so if we wanted to hide details about the original question, about the original function in a recursive binary search, then we might just send the array slice into the function and say, hey, I don't know what came before this, but keep doing that pivot comparison thing for this set of numbers.
Question.
So, yep.
Do we have to keep track of the indices, or is that information in the array slice? So like dot enumerated on an array slice, how would that be able to work?
Yeah, let's try it out. So for, let's say we're looking at the first index here. For the index and the value in split array dot enumerated, let's print the indexes. Oh no. Let's do it on the regular one, sorry. Cool. However, one thing I want to note is, if you remember, this doesn't work. I'm sorry, this doesn't enumerate itself. Just counts from 0. So what we saw in there before was actually my print statement. If I'm just looking at the second array slice, which starts with 7 here, there's one item but enumerated doesn't actually look up indexes. It just starts counting from 0. Which means that on an array slice, if we want the indexes, we can't actually enumerate. Enumerating is, I think it says it explicitly. Yeah. It represents a consecutive integer starting at 0. So it's just counting from 0. So be careful with your array slices. Okay. So guys, this is a bunch of stuff about a binary search. What is this method of problem solving called? Has anyone heard it before?
Divide and conquer.
Yep. Thank you. Divide and conquer. So honestly, if possible, when you can, when someone mentions a divide and conquer situation, first check that the stuff is sorted, because chances are they're saying in some way do a binary search. And if you want to do divide and conquer yourself, do a binary search. What are some questions you have so far? Did we lose someone?
So I have a question. What if the target number isn't actually in the array?
That's a great question. That's definitely an edge case and an important one. Edge case. What if the target is not in the array? How would we handle? How would we handle searching for 10 in, let's say, let me make sure this is resorted. Cool. Well, what would happen if we handle 10 in this search?
You would want to check, after sorting it, you would want to check if your target number is greater than the last number or less than the first, not the last integer in the array, so the last index, and then less than for the first index.
Then, yep, the value of the value at the first index. Sorry. Yeah,
Even-
that's great.
Sorry, even in this scenario, there's still an edge case where the number just isn't in the array. So you could have 1, 2, 3, 4, 5, but say 4 isn't in that array. It could still be sorted.
Yeah. What if the sorted array doesn't contain all items sequentially? 1, 2, 3, 7, 8, 9. Doesn't contain the range of all items sequentially. Cool. So the thing here is using the binary search with just a tiny bit of like error checking is still gonna work. Why would it work? Let's say I'm looking for, I'll make this even bigger.
Can you return like nil?
Yeah, if I'm looking for 16 in that array, I'll make the decision that if it's not in the array, I'll return nil. And how do I get to the point where I know that?
You would want to have already done everything else. So like if you're looking for 16, you would have already looked through the array. And since binary search I think is really convenient runtime, it's not really going to take too much time to go through everything. And then at the end, if it doesn't meet any of the cases, you would just return false.
Yeah. Perfect. So let's go through that scenario real quick. First, I'll pivot from 8, 1 up. Then, because it's larger, let's say I pivot from 10 that's our second op. And then because it's larger than that, let's say when I have an even number, it seems like I've been rounding down. So the target will be 11, and then pivot from 11, third op. Then pivot from 15, fourth op. Then, because there's nothing to the right of 15, I'll have to say it wasn't found. And if you notice, our input was 9 things. We only did 4 operations, and this grows even slower as the size of the input gets larger and larger. So doing a binary search, we rule things out relatively quickly to a linear search. How do we feel about this right now? Okay, so